Artificial Intelligence Incorporation of Regularization. Welcome to PhDAI730 Lecture 12. This is your Professor T. Fareed Muhammad. One of the key techniques we'll explore is regularization methods in this lecture, which are essential for improving the interpretability and predictive power of statistical models in high-dimensional settings. Regularization methods such as lasso, which is least absolute shrinkage and selection operator, and ridge regression introduce a penalty for complexity, thereby preventing overfitting and enhancing model performance. These methods help to manage the complexity of high-dimensional data by shrinkage, the coefficients of less important features, which effectively reducing the model's complexity and improving its generalizability. Through these techniques, we can build more robust and interpretable models that are capable of handling the intricacies of modern datasets. By understanding and applying these methods, we can unlock new insights and make more informed decisions based on complex data. Regularization represents a philosophical shift in how we approach statistical modeling. In the classical paradigm, we seek to minimize prediction error on our training data, trusting that good performance on observed data will translate to good performance on future data. However, this trust is misplaced in high-dimensional settings where artificial intelligence starts incorporating standard statistics. So this is a place where models have enough flexibility to memorize training data rather than learning genuine patterns. Regularization explicitly rejects the goal of perfect training fit, instead adding a penalty that measures model complexity. This penalty could count the number of non-zero parameters, measure their total magnitude, or encode their notion of simplicity. By minimizing combination of training error and complexity penalty, we deliberately accept worse training performance to achieve better generalization. A counterintuitive but essential strategy for high-dimensional success. So the real-world use case we can discuss here is credit card fraud detection systems process hundreds of transactions features where regularization prevents the model from memorizing specific fraudulent patterns in training data, instead learning generalizable fraud indicators that work on new transactions. So the research question here for you to ponder upon is, how can we theoretically characterize the implicit regularization effects of different optimization algorithms like stochastic gradient descent? And do these implicit regularizers offer advantages over explicit penalty terms? So I would strongly suggest you to conduct this research on your own. You can even write a research article on top of this area. The bias variance trade-off. The bias variance decomposition provides the theoretical foundation for understanding why regularization works. Expected prediction error can be decomposed into three components: irreducible noise, which is Bayes error, bias, which is systematic error from model misspecification, and variance, error from sensitivity to training data. Unregularized estimators in high dimensions have low bias. They are flexible enough to fit the true relationship, but catastrophically high variance because small changes in training data cause wild coefficient swings. Regularization inverts this by concentrating or constraining the model, we introduce bias. We can no longer fit certain true relationships, but we dramatically reduce variance by limiting how much estimates can fluctuate. The bias variance trade offs means we are trading one type of error for another. Stock price prediction models with hundreds of technical indicators use regularization to reduce variance in coefficient estimates, accepting slight bias to achieve more stable predictions that don't wildly fluctuate with each new training sample. So, the key insight is that this trade is favorable in high dimensions. When the number of parameters approaches or exceeds the sample size, variance grows rapidly while bias remains modest, making variance the dominant error source. Regularization reduces variance proportionally to how strongly we constrain the model, as mentioned earlier, while bias increases more slowly. There exists an optimal regularization strength where total error, which is bias raised to the power 2 plus variance, is minimized. Too little regularization leaves variance high. Too much regularization makes bias dominate. This optimum shifts with dimensionality. Higher dimensional problems require stronger regularization because variance is more problematic. Modern methods like adaptive regularization attempt to optimize this trade off automatically, applying strong penalties where variance is problematic and weak penalties where bias is the concern, achieving better overall error than uniform regularization. The regularization strength parameter lambda controls the penalty severity, requiring careful selection through methods like cross validation, information criteria like A1C, B1C, or theoretical approaches that depend on noise level and sparsity estimates. Imagine you are programming a robot to follow a black line on the floor. Your robot has sensors that detect how far it is drifting from the line, and you need to decide how aggressively it should correct its steering. If you set the correction strength too low, your robot will be lazy, it will wander all over the place and barely try to stay on the line. But if you set it too high, your robot becomes overly nervous, it will zigzag wildly, overcorrecting every tiny deviation and possibly going completely off track. The turning parameter is like this correction strength setting, the tuning parameter is like this correction strength setting, and selecting the right value means finding that sweet spot where your robots smoothly follow the line without being too loose or too twitchy. In machine learning and statistics, we face the exact same challenge, choosing how strictly our model should follow patterns in the data. The tricky part is that you can't just guess the perfect setting. You need to test it. In robotics, you might run your robot through the course 10 times with different correction strengths, measuring how well it performed each time. Maybe correction strength 3 makes it fall off the line, strength 7 makes it zigzag too much, but strength 5 keeps it smooth and on the track. This testing process is called cross validation in statistics. Just like testing your robot on practice runs before the big competition, data scientists split their data into practice sets and test sets, trying different tuning parameter values to see which one makes the most accurate predictions. The goal is always the same: find the setting that performs best in real situations, not just in your training environment. Too strict and you have memorized every crack in your practice floor but fail on a new surface too loose and you never learned to follow the line properly in the first place. So the research question you can explore is how can we develop Oracle inequalities that prove specific tuning parameter selection methods achieve performance within a constant factor of the ideal Oracle choice across all possible scenarios. Imagine you're building an AI agent that helps students decide if a movie review is positive or negative. Your AI system looks at thousands of words, but here's the key insight: certain words naturally belong together in families. For example, the happy family includes words like happy, joyful, delighted, cheerful, and pleased. They all express similar positive emotions. The sadness family has sad, unhappy, miserable, depressed, and gloomy. Regular lasso is like a picky friend who might randomly choose happy but ignore joyful and delighted, even though they all mean basically the same thing. This creates a weird situation where your chatbot or AI agent learns that happy is important but somehow misses the joyful also signals a positive review. Group Lasso is smarter. It says either the entire happiness word family matters or none of it does. It keeps word families together, so if it decides that emotional words are important for understanding reviews, it will use the whole emotional vocabulary, not just random pieces of it. In practical large language models like Claude, Anthropic Claude, Mistral, the Chat GPT, or DeepSeek, etc., smaller cousins, Group Lasso becomes really useful when you want to make a compact, efficient model for a specific task. Let's say you are creating a spam detector for your school's forum that runs on your phone, so it needs to be small and fast. You start with thousands of words like slang families, so it needs to be small and fast. Slang families, punctuations pattern like or something, etc. Emoji groups, formal language families, and causal or casual speech families. Group Lasso helps you figure out which entire families matter for detecting spam. Maybe it discovers that excessive punctuation groups and urgency word families, now hurry, limited time, are super important for spam, while formal academic word families don't help at all. Instead of keeping random individual words and making your model confusing, Group Lasso cleanly selects or rejects whole meaningful categories. This makes your final spam detector not only more accurate but also easier to understand. You can literally say this model works by checking for urgency, language, and excessive punctuations rather than it uses these 47 random words we can't really explain. That's the power of thinking in groups rather than individuals. Sparse Group Lasso. Sparse Group Lasso combines group penalties with individual sparsity penalties, encouraging sparsity both between groups and within selected groups, providing hierarchical selection that mirrors many real world feature structures, as I just mentioned about the happy and sad aspect. Brain connectivity analysis from fMRI data uses sparse Group Lasso where groups represent brain networks and individual variables are connections, identifying both relevant networks and specific critical connections within these networks. Adaptive lasso applies different penalty weights to different coefficients based on initial estimates using weights inversely proportional to preliminary coefficient magnitudes to reduce bias for large true coefficients while maintaining selection for zero coefficients. The time series forecasting with autoregressive models uses adaptive lasso with weights from ridge regression initial estimates, more accurately identifying true lag dependencies while setting irrelevant lags exactly to zero. So, here is a research question that I would like to pose for you to think about or ponder upon. Under the conditions, those adaptive lasso achieve the oracle property of performing as well as if the true model were known in advance, and how sensitive is this property to initial estimator quality. So conduct Google Scholar research and find out the answer for your extended understanding. Fuse lasso adds penalties for differences between consecutive coefficients in addition to coefficient magnitudes, encouraging both sparsity and smoothness. Particularly useful for ordered variables while neighboring coefficients should be similar. Copy number variations detection in genomic sequences uses fuse lasso to identify rigorous of chromosomal gain or loss, exploiting spatial continuity while allowing sharp boundaries between normal and aberrant regions. Let us take an example of training an AI assistant that understands the emotional tone of a long customer service chat conversation for Amazon, Walmart, Target, whatever. The conversation unfolds over time, message 1, message 2, message 3, and so on up to message 50. Now, human conversation don't usually flip wildly from super angry to extremely happy and back to angry in just 3 messages. Instead, if a customer starts frustrated, they might gradually become calm as the service agents help them, then slowly shifts to satisfied by the end. Regular lasso would analyze each message completely independently, potentially deciding that message 15 is angry, -5 on a happiness scale. Message 16 is delighted, +8, and message 17 is furious, -7. That makes no sense for a real conversation. Fuse lasso is smarter because it adds a special rule, and the rule is not only should I identify when emotions matter, but adjacent messages in the conversation should have similar emotional scores, unless there is really good reason for a sudden jump. It creates smooth emotional curves that match how real humans actually talk. In a practical LLM application, imagine you are building a content moderation system for a discussion forum that flags when conversation or when conversations are turning toxic. You are analyzing 100 comment thread and you want to detect not just individual toxic comments, but when the whole conversation is deteriorating. Fuse lasso helps by modeling toxicity as a smooth signal across the comment sequence. Maybe comments 1 to 20 are friendly, toxicity is 0. Then comments 21 to 35 gradually become heated, toxicity slowly rising from 0 to 3. Comments 30 to 60 are consistently hostile, toxicity stays around 7 to 8. And finally, comments 61 to 100 calm down, toxicity gradually decreasing back to 1. Instead of treating comments 42 as complexity independent from comment 41. So Fuse lasso says These are probably similar because they are right next to each other in the thread. This appearance in reality produces a much clearer picture. You can identify exactly where the conversation started going bad around comment 21 and when it cooled off around comment 61 because we had 100 comments to traverse through. Rather than getting random noisy predictions that bounce all over the place, it is like drawing a smooth curve through the conversation's mood rather than playing connect the dots and widely scattered points. Nuclear norm regularization for matrix penalize or penalizes the sum of singular values, promoting a low rank solution analogous to how L1 penalties promote sparsity. We discussed that earlier. Useful for matrix completion and multitasking problems. Collaborative filtering is recommendation in recommendation systems uses nuclear norm regularization to complete partially observed user item rating matrices. Assuming user preferences lie in a low dimensional latent spaces captured by leading singular vectors. Here's a research question for you to ponder upon. What are the exact sample complexity requirements for nuclear norm minimization to recover low rank matrices from noisy observation, and how do these scale with matrix dimensions, rank, and coherence parameters? So think about it and conduct a research. Graphical lasso estimates spare inverse covariance matrix by maximizing penalized log likelihood with L1 penalties on off diagonal elements where 0 in the inverse covariance correspond to conditional independence relationships and Gaussian graphical models. Financial systematic risk analysis uses graphical lasso to estimate sparse networks of financial institutions, identifying which pairs of banks have direct dependencies versus indirect correlation throughout or through intermediaries informing regular oversight. Square root lasso. Square root lasso modifies the standard lasso objectives by using the square root of the sum of squared residuals, making the optimal tuning parameter choice independent of unknown noise variance, which is sigma square. Industrial quality control applications use square root lasso when measurement error variance is unknown and difficult to estimate, as the method automatically adapts to noise level without requiring variance estimates for parameter tuning. Relaxed lasso is a two-stage procedure that first applies lasso for variable selection, then rifts or refits or rifts, and the model on selected variables without penalty or with reduced penalty, reducing bias while maintaining selection benefits. So the example here is environmental modeling, selecting pollution sources from hundreds of candidates uses relaxed lasso to first identify relevant sources, then obtain unbiased effects estimates for policy analysis by refitting without shrinkage. Stability selection. Stability selection runs regularization algorithms on random subsamples of data repeatedly, selecting variables that appear consistently across subsamples, providing finite sample error control without asymptotic assumptions. So, in the life sciences arena, biomarkers discovery in clinical proteomics uses stability selection to identify proteins that reliably predict disease across 100 bootstrap samples, ensuring discovering or discovered biomarkers are robust rather than artifacts of specific data splits. How can we extend stability selection frameworks to provide simultaneous control to both false discovery rate and false negative rate while maintaining computational feasibility for ultra high dimensional problems? So that's a good question for you to answer. Proximal gradient methods. Proximal gradient methods solve regularized optimization problems by alternating between gradient steps on the smooth loss component and proximal operators on the non-smooth penalties, providing efficient algorithms with convergence guarantees. Real-time video processing applications use proximal gradient algorithms for sparse reconstruction, processing 30 frames per second by exploiting the separability of L1 penalties through soft thresholding proximal operators. Coordinate descent for lasso. Coordinate descent updates one coefficient at a time while holding others fixed, being particularly efficient for lasso due to closed form soft thresholding updates, often outperforming general purpose optimization methods for sparse problems. Large scale text classification with millions of features uses coordinate descent lasso implementation that exploit feature sparsity, training models in minutes rather than hours compared to gradient-based method. Future directions in regularization. Emerging directions include learning regularization functions from data, developing regularizers for complex structures like tensors and networks, integrating regularization with causal inference, and understanding implicit regularization in neural networks. Automated machine learning platforms are incorporating meta learning approaches that predict optimal regularization strategies from dataset characteristics, reducing the need for extensive hyperparameter tuning across different applications. Hope this has given you ample thought process to establish understanding the regularization techniques. And I would see you in the next lecture. Happy learning.